Alright, so this video is going to be part 5 of our sequences and series review. So this is going to be the first of 3 videos dedicated to our series tests. So just seeing if a series converges or diverges. Now before we get into the first of our tests, what we need to do is go over the geometric series and the p-series and when they converge and diverge, because that can help you to where you don't have to go through your tests. Now first, we have our geometric series. And this takes on the form the sum from n equals 1 to infinity of a times r to the n minus 1. Now, this series would converge when r is between -1 and 1. Okay, so it's all dependent on your common ratio right here. All right? So, yeah. Now, what about the p-series? Now the p-series takes on the form the sum from n equals 1 to infinity of 1 over n to the p power. That's why it's called a p-series, okay? Because it's all dependent on this p here. As with the geometric series, it was dependent on the common ratio r. So for the p-series, it converges when p is greater than 1, and it diverges when p is less than or equal to 1. If the absolute value of r is greater than 1 or equal to 1, then this geometric series is going to diverge. Okay, so I should have kind of included that too. Diverges when the absolute value of r is greater than or equal to 1. So you can see here that it's kind of the opposite. The geometric series diverges when the absolute value of r is greater than or equal to 1, and the p-series diverges when p is less than or equal to 1. So it's kind of the opposite. Now, here's an example, quick. If we had the sum from n equals 1 to infinity of 1 over, let's say, n squared, is that going to converge or diverge? Well, our p is 2 there, and that's greater than 1, so it's going to converge. What about if I gave you the geometric series, the sum from n equals 1 to infinity of 1/10 times 3/10 to the n minus 1? Well, there, your common ratio is 3/10, and that is going to be in between -1 and 1, so it's going to converge. Okay, so both these series will converge, and those are your nice little examples there. So our first test is the test for divergence, and if the limit as n approaches infinity of your a sub n, if you're not sure what your a sub n is, your series looks like this, the sum of whatever of a sub n. Whatever is right here in this area is your a sub n. Okay? So if that's not equal to 0, okay, the limit of your a sub n, well, then your series is going to be divergent by the test for divergence. All right, here's a quick example. Now, if we had the sum from n equals 1 to infinity of 2n squared plus 3 all over 3n squared plus 5n plus 2, well, we can actually figure out if this is going to converge or diverge by the test for divergence. Because, and by the way, I may have misspoke there. The test for divergence does not prove convergence, okay? It will never prove convergence, it only proves divergence, okay? But if the limit does equal 0, then you just got to keep going, keep trying other tests, okay? You can't just say it's convergent, okay? The test for divergence only proves divergence. That's you know, that kind of makes sense because of the name. Now, the limit as n approaches infinity of 2n squared plus 3 over 3n squared plus 5n plus 2, well, you can just look at the highest power of n on the top and bottom. That's going to be, well, a 2 on the top because our highest power is n squared, and we have a 3 on the bottom. So this limit is just going to equal 2/3. 2/3 is not equal to 0. So this series diverges by the test for divergence. Now here is our next test. This is the integral test, okay? So we want to represent a sub n as f of x, and we want to integrate that, Okay, so if the sum of your a sub n, if your a sub n looks like it can be integrated, then the integral test is a great thing to use. Now, if the integral of f of x dx, because you're representing, and I'll show you an example of this in a little bit, if you represent your a sub n as f of x and you integrate it, if the integral of f of x dx is convergent, then your series is going to be convergent. If the integral is divergent, then your series is divergent. And a big note here, don't forget this, you can only integrate on an interval where your f of x is positive, continuous, and decreasing. Okay? You're not going to be able to integrate from 1 to infinity if maybe your f of x has a discontinuity at 3. Okay? Well, then try, if that's the case, try from 4 to infinity. Okay? It's not going to be divergent from 1 to 3. Okay? You know that. So, all you really care about is this infinity here, that infinity bound. Okay? That's what matters. It really doesn't matter too much what your starting bound is. Okay? So, that's something to keep in mind. We're going to do an example, and that's going to be it for this video. Now here we have the sum from n equals 1 to infinity of n over n squared plus 1. Okay? Now, this n over n squared plus 1, we can represent that, okay, we can represent our a sub n as f of x. Okay? We can represent our n over n squared plus 1 as x over x squared plus 1. And what we can do is we can integrate this. Okay? Which is the same thing as adding up all the terms. Okay? We're adding up all the terms of x over x squared plus 1. Okay? Let's try from 1 to infinity. So we want to be able to have this integral over here from 1 to infinity of x over x squared plus 1 dx. To be able to have those bounds, though, we need to make sure that f of x is going to be positive, continuous, and decreasing. Well, first off, the easiest one, I guess, is it going to be positive? Well, yeah, I mean, x cannot be negative. We're integrating from 1 to infinity, so it's not going to be. Okay, and when we have x squared, which of course is always going to be positive, and we have plus 1. So we only have all positive terms, so we basically know that it's going to be positive, so we can put a nice check mark right there. Now what about continuous? Is there going to be any discontinuities? Well, look at this denominator. Is there anywhere where it could be 0? And the answer is no. Okay, so, okay, cool. It's continuous. Now lastly, we want to see if this thing is decreasing, and we can tell that by, well, let's see if this a sub n is decreasing. Okay, let's look at the next term in that series, and well, that's going to be n plus 1, right? So if we're dealing with n, let's look at the next term, which will be n plus 1. We plug in n plus 1 for n, we get n plus 1 over a n plus 1 quantity squared plus 1. So, okay, so just plugging in a n plus 1 everywhere we see an n. Now if we do a little bit of foiling here on the bottom, and we combine like terms here, we're going to get n plus 1 over n squared plus 2n plus 2. And now what is the relationship going to be? Has the denominator changed by more? Okay? Or has the numerator changed by more? Well, you can see here that the numerator has only changed by 1. Okay? Whereas the denominator, you've added 2n to it, and you've also added 1. So obviously the denominator has changed more, okay, than the numerator, and you can tell that. So now the denominator is bigger. All right, and what that means is that this whole thing is going to be smaller than this. All right, so you can see that it is decreasing, and that means that we can actually do this integral. So let's do it. Now, if we wanted to do this integral, we gotta take a limit as t approaches infinity. Remember how we do improper integrals here. Of the integral from 1 to t of, this will be a x over x squared plus 1 dx. Now we can do a u substitution, right? We can do a u substitution, and we'll set u equal to x squared plus 1, right? Because then du is going to be 2x dx. We don't have a 2 here, so let's divide that off, and we get that du over 2 is equal to x dx. All right? So, great. Now we have our substitution, but we got to figure out what is going to happen to our bounds. All right? So, when x equals 1, what happens to u? Well, u is going to equal, well, we plug in 1 for x here, and we get 1 plus 1, which is 2. And when we have x equal to t, we're talking about an infinitely large number here. So it doesn't matter these little small things you do to it, like squaring it and adding 1, u is going to equal t as well. Okay, an infinitely large number. Okay, so now we can just plug in, all right? We can plug in, and we get the limit as t approaches infinity of, let's pull out this over 2, we'll have a 1/2 the integral from 2 to t of, this is now just going to be, because the x dx goes away with the du over 2, and the x squared plus 1, that was our u. So we get 1 over u du. Okay, integrating that, we get the limit as t approaches infinity of 1/2 natural log absolute value of u evaluated from 2 to t. Okay, now doing our evaluation step, this is just going to be the limit as t approaches infinity of 1/2 times natural log absolute value of t minus natural log absolute value of 2. Okay, and you can see here that that is obviously going to diverge because t is approaching infinity, so you're going to get an infinitely large number here, and that will make the whole thing infinitely large. Okay, doesn't matter that you're subtracting natural log of 2. It doesn't matter that you're multiplying by 1/2. It's still going to be infinitely large. Now, so that's going to equal infinity, okay? And that means that this integral diverges. And that all means that this series is divergent by the integral test. And that is going to do it for this video.
So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series and the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.